Hello everyone, my name is Fangrui. I'm a graduate student of Beijing Institute of Technology. This work proposes a domain convex game framework for improving model generalization, aiming to ensure the strictly positive correlation between model generalization and domain diversity, thereby guaranteeing and further enhancing the validity of domain augmentation. We first recast DG as a convex game between domains, and then encourage each diversified domain to enhance model generalization by elaborately designing a regularization term based on supermodularity. Meanwhile, we construct a sample filter to eliminate low-quality samples, thereby avoiding the impact of potential harmful information. Extensive experiments demonstrate the rationality and effectiveness of DCG. First, we introduce the background. Domain generalization aims to generalize the knowledge learned from multiple labeled source domains to an unseen target domain. Note that the distributions of all the training and testing domains are different from each other, which is common in the real-world applications. Here is an example in BACS dataset, where we take sketch, cartoon, and art painting domains as training set, and the leave out photo domain as test set. A classical solution to domain generalization is domain augmentation, the common belief of which is that diversifying source domains will be conducive to the auto-distribution generalization. However, these claims are understood intuitively rather than mathematically. Our explorations empirically reveal that with the increase of domain diversity, the model generalization may not necessarily increase, but sometimes decreases instead, as the solid lines in this figure show, which limits the effectiveness of domain augmentation. We therefore aim to ensure the strictly positive correlation between model generalization and domain diversity, as the dashed lines in this figure show, thereby guaranteeing and further enhancing the validity of domain augmentation. Considering that convex game requires each player to bring profit to the collision, which is consistent to our insight. That is, make each diversified domain bring benefit to model generalization. We propose to recast domain generalization as a convex game between domains. Given P original domains, we first prepare Q augmented domains using Fourier augmentation technique, which mixes the amplitude spectrum of a pair of samples by linear interpolation to synthesize augmented instances from lower domains. Then, we randomly split the original domains into meta-train and meta-test domains. Next, we pick out the augmented domains generated by data in current meta-train domains, and incorporate them into the meta-train domains. By randomly sampling from meta-train domains, we can obtain collisions S and T, and obtain their union and intersection naturally. Thus, we are ready for constructing convex game between domains. Based on the supermodularity property of a convex game, we design the profit V for each collision as the obtained model generalization ability after training on this collision, which is measured by the meta-test loss on meta-test domains. Then, we can obtain the supermodularity regularization term as follows, by optimizing which we can encourage each diversified domains to enhance model generalization. In addition, to eliminate low-quality samples to further avoid the effect of harmful information, we try to detect the samples that contribute more to the above supermodularity regularization, that is, more unfavorable to our goal. Specifically, we measure the contribution of each input by multiplying the input and the corresponding gradient produced by the regularization loss. Then, we pick out the samples with the top K contribution score and cast them away when calculating the supervision loss. The overall optimization objective is as follows. We can see DCG achieves SOTA model generalization on both PACS and Office Home benchmark, and the generalization study demonstrates the effectiveness of each part in our framework. Besides, with the increase of domain diversity, the model generalization of DCG increases monotonically on the whole, and the decrease of marginal contribution of domains is alleviated, demonstrating the effectiveness of conducting convex scheme between domains. Finally, we provide example samples that with top K and bottom K score. We can see that the filter samples either be noisy images or be redundant images, while the returned samples are all vivid and rich in information, which verifies the effectiveness of our sample filter. Thanks for your interest in our work. The source code is available and feel free to get in touch with us if you have any questions.